Hello, I'm Jisung, a postdoc in Safari Research Group at ETH Zurich. In this talk, I would like to present Evanesco, architectural support for efficient data sanitization in modern flash-based storage systems. This work is collaborated with Seoul National University and Safari Research Group, and it appears in ASPLOS'20. Here is a summary of this work. Secure deletion is essential in storage systems, as modern computing systems process a large amount of security-sensitive data. However, it is challenging to support data sanitization in NAND flash-based SSDs, because an SSD does not overwrite stored data due to the erase before write property of NAND flash memory. Existing solutions based on physical data destruction introduce significant performance and reliability overheads in modern SSDs. We propose Evanesco, a low-cost data sanitization technique without reliability issues, which uses on-chip access control mechanisms. It manages access permission flags inside the NAND flash chip so that the chip itself can prevent access to data if the access permission flag is disabled. Evanesco ensures that an access permission flag cannot be reset to enabled unless the data is erased. Using 160 real 3D NAND flash chips, we confirmed that Evanesco does not incur any reliability issue. An Evanesco-enabled SSD significantly reduces data sanitization overheads, providing comparable performance with an unmodified SSD. Here is the outline of this talk. I will first review the challenges in secure deletion in modern SSDs with brief background of NAND flash memory. Modern computing systems process a large amount of security-sensitive data, such as private message, private photos, and confidential data like medical records. To avoid malicious access to such data, a storage system should guarantee that once a user intentionally deletes data, the data becomes irrecoverable. However, in a NAND flash-based SSD, the old versions of an updated or deleted file can remain in the SSD for a very long time. To better understand this data versioning problem, we measured the amount of valid and invalid pages inside an SSD when a file is heavily updated. While updating the file, the number of valid pages remains the same, but its invalid pages rapidly increases as long as there is a free space in the SSD. When free space runs out, the number of invalid pages starts to decrease, but the speed is very slow. Such a large amount of updated or deleted data remaining in the SSD is mainly due to unique features of NAND flash memory. In NAND flash memory, multiple cells form a NAND string, which is connected to a bit line. Cells at the same location of different bit lines, which is called a page, have to be read and programmed at the same time. Pages at the same NAND strings comprise a block, which is the unit of erase operations, and multiple blocks share bit lines and peripherals. These unique organizations and operation mechanisms result in the erase before write property that an entire block needs to be erased before programming its pages. In other words, a flash page cannot be overwritten directly. An SSD commonly employs a special firmware called FTL to provide backward compatibility with hard disk drives that support overwrites. FTL distributes host writes to flash chips to fully exploit the internal parallelism of the SSD. If a file system updates logical pages, FTL performs out-of-place updates using free pages. FTL should maintain mapping information between logical and physical pages to service future read requests. To sustain free pages for future writes, FTL triggers garbage collection when it runs out of free pages. It selects a victim block that has the least number of valid pages, because the valid pages should be moved to other free pages before erasing the victim block. For doing so, FTL should also keep track of the status of each page. Let's see what happens in an SSD when the file system deletes or updates a file. Most file systems delete a file by removing the file's metadata, and FTL invalidates the related physical pages by just updating their status while leaving the actual contents intact in flash chips. If a file system overwrites a logical page, FTL performs an out-of-place update, which also leaves the old data intact. These embedded pages remain in the SSD indefinitely until garbage collection erases the corresponding blocks. In fact, this deletion mechanism can also provide some protections against the malicious access to stale data. An adversary cannot retrieve old data through a file system, since the file system has already removed the links between the file and logical pages. Even with direct access to the SSD, the adversary cannot read the deleted data using standard I/O interface, because FTL also deleted the mapping information of the embedded pages. However, if the adversary can dissolve the raw NAND flash chips and access them using a custom flash controller, he or she can directly read the contents of embedded pages remaining in the flash chips. In this case, by using a file recovery tool, entire deleted files and previous versions of updated files can be easily recovered. The most intuitive way to address this problem is to erase a block immediately after a page is invalidated. However, to erase a target page, we should first move all the valid pages in the corresponding block. If the block has free pages, they should be erased without programming. These are large amount of copy operations and wasted pages, significantly degrade the performance and lifetime of the SSD. To address this, prior work proposed scrubbing that reprograms all the cells stored in an invalid page to destroy the page contents without a block erasure. However, it also incurs performance and lifetime overheads in modern NAND flash memory that stores multiple pages in the same flash cells. As scrubbing destroys all the pages stored in the same cells, it needs to copy all the valid pages before performing scrubbing. Even if we can afford the copy overheads, cell-to-cell interference during scrubbing significantly affects the data reliability of adjacent cells. In summary, existing solutions are hard to adopt in modern SSDs due to performance, lifetime, and reliability problems. Next, I will introduce Evanesco, a new low-cost data sanitization technique for modern SSDs. Our key idea is to allow a NAND flash chip to be aware of the validity of each page, so that the chip itself can prevent access to invalid pages. Evanesco does not touch flash cells that store user data, so it can avoid copying valid pages and affecting reliability of stored data. To this end, we propose two new NAND flash commands, page lock and block lock. When a page is invalidated, the plock command disables its access permission flag. If a block needs to be sanitized, the block command disables all the pages in the block. Even if an adversary directly accesses the raw flash chip, the chip just returns dummy data for an access to invalid pages. Let's dive into our plock implementation. We implemented the access permission flag of each page using spare cells, which exist in most NAND flash memory to store page-related metadata. We use spare cells to store the access permission flag of each page, such that a page is enabled when the flag cell is erased, and a page is disabled when the flag cell is programmed. This ensures that a disabled page cannot be re-enabled until the entire block, including the page's content, is physically erased. No additional command is required to read the access permission flag, as it is read together with the page data at the same time. We slightly modify the read data path in NAND flash memory by adding bridge transistors that are controlled by the value of flag cells. Once a plock command programs the flag cell of a page, the page data cannot be read as bridge transistors disconnect the page buffer from the data out circuitry. Let me show more details of our plock implementation to address challenges in modern NAND flash memory. As explained, modern NAND flash memory stores multiple pages in the same cells. To support the per-page sanitization, we keep multiple access permission flags on each row. Another problem is that a flag cell can misbehave, which incurs unintentional disabling or enabling of a page. To avoid this, we use multiple cells for each access permission flag. In our implementation, plock supports copy-free and per-page sanitization without cell-to-cell interference to other cells. However, there are still potential reliability issues due to cell-to-cell interference between flag cells in the same stream, and program disturbance due to high programming voltage applied to the other cells in the same row. To address this, we use flag cells in single-level cell mode and programming them by one-shot programming scheme with low voltage, which significantly reduces the impact of program interference and disturbance. Please find more details of these optimizations in our paper. In summary, plock can sanitize a page without copy overhead and reliability issues. Next, let me introduce the plock implementation. Even though plock does not require copy operations, it may incur non-trivial performance overhead to sanitize a large number of pages at the same time, which happens during large file deletion or SSD management tasks. For example, deleting a 1 GB video requires 64K plock operations, assuming a page size of 16 kilobytes. Even if a block has no valid pages, it is not feasible to erase a block immediately due to a reliability issue in modern 3D NAND flash memory called the open block problem. The open block problem is a reliability degradation due to a long time interval between erasing and programming a block, which changes the electrical states of erased cells as if programming them slightly. To avoid this, a block should be erased lazily just before programming new data to the block. We measure the raw bit error rate of a block in different program and erase cycles and retention times while increasing the open interval. And it turned out that a long open interval can increase the error rate by more than 30% when the block experiences large P cycles and retention time. We implement the block command to disable all the pages of a block at once without physically erasing the actual contents by exploiting a new feature of 3D NAND flash memory. As explained, bin lines are shared by multiple blocks, so it is necessary to activate only one block for each operation. To this end, there is a group of transistors at the top of each block called the string select line, which allows us to selectively activate a block by applying appropriate voltages to SSLs. Modern 3D NAND flash memory implements an SSL using flash cells that can also act like a typical transistor. A block command programs the SSL of a block, which increases the threshold voltage of flash cells in the SSL. Once the SSL is programmed, it cannot be turned on with normal voltage, which effectively disconnects entire pages in the block from the page buffer. For any page read on a disabled block, this prevents current flow through NAND strings in the block, so the page buffer data is set to 0 regardless of the actual data. Since there is no way to delete only the programmed SSL, block disables access to all the pages until the block is physically erased. Finally, we design an Evanesco-Enabled SSD called SecureSSD. SecureSSD supports immediate data sanitization at the storage level whenever pages need to be invalidated. Once the host system deletes or updates the file, log manager issues plock and block commands depending on the block's status. If there are valid pages in the block, it performs a plock command. When there is no other valid pages in the block, a block command sanitizes multiple pages at once. SecureSSD also supports selective data sanitization to avoid unnecessary plock or block commands for security-insensitive data. It enables a user to set low security requirements of written data by using extended I/O interfaces. For a physical page that stores the security insensitive data, SecureSSD sets the page status to insecure to invalidate such a page without performing plock or block command. By doing so, SecureSSD minimizes performance overheads of data sanitization. Next, I will show our evaluation results. We first validated plock and block commands using 160 real state-of-the-art 3D TLC NAND flash chips. We found the best operation parameters of plock and block operations, which provide much shorter latency than the program latency without degrading reliability. For system-level evaluations, we implemented the SecureSSD using an open SSD development platform. We compared the SecureSSD with the two SSDs that use existing data sanitization techniques. Once a page needed to be sanitized, Erase SSD immediately erases the entire block after copying all the valid pages in the block. Scrubbing SSD immediately performs a scrubbing for a page after copying all the valid pages in the same cells. We used 3 server workloads and 1 mobile trace in our evaluations. We measured the input-output operation per second of each SSD. All the values are normalized to that of an unmodified SSD without data sanitization support. As the graph shows, SecureSSD provides comparable performance with an unmodified SSD, while existing solutions significantly degrade the SSD performance due to a large amount of copy operations for valid pages. So, SecureSSD significantly reduces performance overhead of data sanitization. We measure the write amplification factor of each SSD to compare the lifetime overhead. In y-axis, we normalized the WAF value of each SSD to that of an unmodified SSD. The lower WAF, the better lifetime the SSD can achieve. As you can see, existing techniques significantly increase the number of written pages for copying the associated valid pages. In contrast, as a SecureSSD does not introduce additional copy operations, it can provide the same lifetime as an unmodified SSD. We measure the IOPS performance of SecureSSD while changing the fraction of security-sensitive data. As expected, the less security-sensitive data, the higher performance SecureSSD can achieve. By avoiding unnecessary sanitization for security-insensitive data, SecureSSD minimizes performance overheads of data sanitization. Please also see our paper for more detailed analysis and evaluations. There we provide an empirical study on how much and how long invalid data can remain inside SSDs, and show the reliability impact of existing physical data destruction schemes using real NAND flash chips. We also provide extensive design space exploration results and evaluate the performance benefit of using the block command. Let me conclude my presentation. In this talk, we presented Evanesco, a new low-cost data sanitization technique for modern NAND flash-based SSD, which uses on-chip access control mechanisms. For page-level sanitization, we propose a page lock that manages the access permission flag of each page using spare cells. For block-level sanitization, we propose a block lock that programs the SSL of a block to disable all the pages in the block at once. We also propose a SecureSSD that supports a selective data sanitization to minimize performance overheads. Our evaluation results show that SecureSSD significantly reduces performance and lifetime overheads without any reliability issues. We encourage you to read our paper for more details, a link to which is provided under this video. Thank you for watching my talk.